Hello, I am Amlene. Welcome to my general mathematics class.
Lesson 1. Representing real-life situations using logarithmic functions. Okay, let's start with a recall. Okay, this example is our present situation. Laboratory findings show that SARS-causing coronavirus, upon reaching maturity, divides itself into two every hour. How many cells of the virus will be present after 1 day when it started with just one cell? So let us solve the given problem. First thing to do is to assign the variable t be the number of hours elapsed. Function f of t be the number of coronavirus present after 1 hour. Now the solution can be represented by using the table of values. So this is our table of values where the first row is for the t, variable t, for time. The second row will be the function f of t, that is the number of coronavirus present after 1 hour. So initially, the number of coronavirus cell is 1, or the coronavirus started with a single cell. Now, based on the description or based on the given problem, the virus divides itself by 2 after every hour. So at time 1 hour, the number of cells of the coronavirus is 2. Then after 2 hours, it's 4. Then after 3 hours, it's 8. Then 4, 16. Then at 5 is 32. And at 6 hours, there will be 64 number of cells coronavirus. Based on our table of values, the table shows a pattern. As t increases by 1, function f of t increases rapidly by 2 raised to t. In symbols, function f of t is equal to 2 raised to t. So this function will be the mathematical model of our problem. Now imagine if t is equal to 24 hours, that is for 1 day. Substituting the value of t to our mathematical model, we have f is equal to 2 raised to 24 is equal to 16,777,216. In a matter of 1 day, a virus that started as a single cell can increase 2 millions of cells, each of which has the same ability to reproduce exponentially. So this given real-life situation is one of the applications of exponential functions. Now we're going to start. Now let's discuss further about logarithmic expression. Here's a table of transforming exponential equation to logarithmic equation. Now, if we're going to recall the form of exponential equation, we have a is equal to b raised to c. Example, we have 2 raised to 2 is equal to 4. Now, 2 is b, which is the base. Then the exponent 2 is the value for c, and 4 is the value of a. Now, in logarithmic equation, its equivalent is, and this is read as log of 4 with base 2 is equal to 2. Now, let's compare the parts of the logarithmic equation to the exponential equation. So, as you notice, we have 4 is the value of a, the base 2 is the value of b, and 2 is the c, which is the exponent. Now let's see other examples. We have 3 raised to 4 is equal to 81 in logarithmic equation. This log of 81 with base 3 is equal to 4. 9 raised to 1/2 equals 3. Log of 3 with base 9 is equal to 1/2. Here are some set of examples. We have n raised to 3 is equal to 64. In logarithmic equation, the log of 64 with base n is equal to 3. 4 raised to 1/2 is equal to 2. Log of 2 with base 4 is equal to 1/2. A raised to x equals y. Log of y with base a is equal to x. So what is logarithmic expression? The logarithm of a number. Let a, b, and c be positive real numbers such that b is greater than 0 and b is not equal to 1. The logarithm of a with base b is denoted by log of a with base b and is defined as c is equal to log of a with base b if and only if a is equal to b raised to c in exponential form. So let's take note that logarithmic functions and exponential functions are inverses. In other words, the inverse of logarithmic function is the exponential function, as well as the inverse of exponential function is the logarithmic function. So, ibig sabihin lang nun, kung ano man yung domain and range ng ating logarithmic function, that will be interchange pagdating po sa exponential function. That is, the domain of the logarithmic function will be the range of the exponential function. The range of the logarithmic function will be the domain of the exponential function, or vice versa. Okay? Now, second, in logarithm form, log of a with base b cannot be negative. So, yung base po natin cannot be a negative value. Lastly, the value of log of a with base b, which is c, and that is the exponent, can be a negative. So, siya lang po pwedeng maging negative. Not like sa base, di po siya pwedeng maging negative. Okay, let's do this exercise. Rewrite the following exponential equations in logarithmic form whenever possible. Here are the examples. First, we have 7 raised to 2 is equal to 49. In logarithmic form, we have log of 49 with base 7 is equal to 2. Next, we have 27 raised to 1/3 is equal to 3. In logarithmic form, the log of 3 with base 27 is equal to 1/3. Next, we have quantity m minus 2 raised to 3 is equal to x. It's logarithmic form. The log of x with base m minus 2 is equal to 3. Lastly, we have e raised to x is equal to 3. So we have an Euler function here. So if we're going to transform this into logarithmic form, we can write this as, log of 3 with base e is equal to x. Now this form is equivalent to natural logarithm. So we are going to rewrite this in logarithmic form. Ln of 3, or natural logarithm of 3, is equal to x. Next set of examples, we have 1/2 raised to negative 2 equals 4. In logarithmic form, we have log of 4 with base 1/2 equal to negative 2. Next, we have the quantity square root of 7 raised to 2 is equal to 7. In logarithmic form, the log of 7 with base square root of 7 is equal to 2. Next, 5/2 raised to negative 2 is equal to 4 over 25. Logarithmic form, we have log of 4 over 25 with base 5/2 is equal to negative 2. Lastly, we have 81 raised to 1/2 is equal to 9. Logarithmic form, the log of 9 with base 81 is equal to 1/2. Now let's do the other way around by rewriting the following logarithmic equations into exponential forms whenever possible. Here are the examples. First, the log of 81 with base 3 is equal to 4. In exponential form, we have 3 raised to 4 is equal to 81. Log of mn, or m times n, with base x is equal to p. In exponential form, x raised to p is equal to m times n. Log of 5, or common logarithm 5, is equal to m. So this form here, as you can see, wala po siyang base. Ibig sabihin po nun, ang base po nito ay 10. So it is known as the common logarithm. So this is in the form of log with base 10. This is known as the common logarithm. Now in common logarithm, given in common logarithm, log 5 is equal to m. In exponential form, it is 10 raised to m equals 5. Next, we have the log of 1 over 16 with base 2 is equal to negative 4. Exponential form, we have 2 raised to negative 4 is equal to 1/16. Next set of examples, we have the common logarithm of 0.00001 is equal to negative 5. So since this is a common logarithm, ibig sabihin nun, its base is 10. So in exponential form, we have 10 raised to negative 5 is equal to 0.00001. Next example, we have a natural logarithm. Natural logarithms of 7 is equal to a. Now, as I've said earlier, ln is equivalent to log with base e. So therefore, in exponential form, its base is e. So e raised to a is equal to 7. Next, we have the log of 13 with base 169 is equal to 1/2. In exponential form, we have 169 raised to 1/2 is equal to 13. Last example, we have log of 3 with base 3 is equal to 1. In exponential form, is 3 raised to 1 is equal to 3. Okay, let's do this exercise. Find the value of each logarithm. So when we say find the value of each logarithm, we are looking for the value of c, or the value of the exponent. Okay, so let's try this. Okay, here are the set of examples. We have log of 64 with base 2. So think of an exponent with base 2 that will give you the value of 64. Okay, it's 6. Now, if we're going to transform this to exponential form, we have 2 with exponent 6 is equal to 64. Next example, we have log of 256 with base 4. So what exponent with base 4 that will give you the value of 256? Okay, we have 4. So if we're going to transform this to exponential form, we have 4 raised to 4 is equal to 256. Next, we have the log of 32 with base 1/2. So what exponent with base 1/2 will give you the value of 32? Okay, so it's negative 5. So if we're going to transform this, we have 1/2 raised to negative 5 is equal to 32. Or if we're going to simplify this, we have 2 raised to 5 is equal to 32. Next example, we have the log of 3 with base 9, or 1 over 9. What exponent with base 1 over 9 will give you the value of 3? Okay, it's negative 1/2. So transforming this to exponential form, we have 1/9 of raised to negative 1/2 is equal to 3. Or we have 9 raised to 1/2 is equal to 3. Or the square root of 9 is equal to 3. Here are the next set of examples. First, we have log of 81 with base 3. What exponent that will give you a value of 81 with base 3? Okay, it's 4. So if we're going to transform this into exponential form, we have 3 raised to 4 is equal to 81. Next example, we have the common logarithm of 1000. What exponent with base 10 that will give you the value of 1000? Okay, yes, it's 3. Transforming this to an exponential form, we have 10 raised to 3 is equal to 1000. Next example, we have another common logarithm of 1 over 1000. Okay, yes, its exponent is -3. And its equivalent in exponential form, we have base 10 with exponent -3 is equal to 1 over 1000. Last, we have the log of 16 with base 0.5. What will be the exponent with base 0.5 if the value is 16? Or that will give you a value of 16. Okay, yes, it's -4. Now, transforming this to exponential form, we have 0.5 raised to -4 is equal to 16. So we can transform this decimal value 0.5 to fraction. Okay, if we're going to transform this, the equivalent is 1/2 raised to -4 is equal to 16. Applying the rule of exponents, we have 2 raised to 4 is equal to 16. So that's it for the basic about exponential expression. Now we proceed with the real-life applications of logarithm. We have here the Richter scale. The Richter magnitude scale was developed in 1935 by Charles F. Richter of the California Institute of Technology as a mathematical device to compare the size of earthquakes. The magnitude of an earthquake is determined from the logarithm of the amplitude of waves recorded by seismographs. The magnitude R of an earthquake is given by this formula. R is equal to 2/3 times log of E over 10 raised to 4.4, where E is in joules, is the energy released by earthquake. The quantity 10 raised to 4.40 joules is the energy released by a very small reference earthquake. The formula indicates that the magnitude of an earthquake is based on the logarithm of the ratio between the energy it releases and the energy released by a reference earthquake. We have here example 1. Given a situation, suppose that an earthquake released approximately 10 raised to 8 joules of energy. A. What is the magnitude on a Richter scale? B. How much more energy does this earthquake release than the reference earthquake? For the solution, let us first perform what is asked on letter A. Since E, which is the energy, is equal to 10 raised to 8, substituting the value of E to our Richter magnitude scale formula, R is equal to 2/3 of the log of the quotient of 10 raised to 8 and 10 raised to 4.4. So in applying the rule of exponent of quotient, we just simply subtract the two exponents, the exponent of the numerator by the denominator, which is 8 minus 4.4. So that will give you 2/3 of the log of 10 raised to 3.6. So ito pong 3.6 ay galing po sa 8 minus 4.4, which is 3.6. Now, since by definition, the log of 10, 3.6 is the exponent by which 10 must be raised to obtain 10 raised to 3.6. So log, or the common log of 10 with raised to 3.6 is simply the value of 3.6. Now, computing, we have R is equal to 2/3 times the log of 10 raised to 3.6. That is 2/3 times 3.6. So, ito po ay equivalent lang po sa 2/3 times 3.6. Multiplying these two will have approximately 2.4. So next we solve what is asked on letter B, that is the many times or the how many times more energy than the reference earthquake. So we have the earthquake releases, that is 10 raised to 8 over 10 raised to 4.4, which is equivalent to 10 raised to 3.6. Using your calculator will give you approximately 3,981 times more energy than the earthquake reference. Okay. Next application of logarithm is the sound intensity in decibel. The loudness of a sound is expressed as a ratio comparing the sound to the least audible sound. The range of energy from the lowest sound that can be heard to a sound so loud that it produces pain rather than the sensation of hearing is so large that an exponential scale is used. The lowest possible sound that can be heard is called the threshold of hearing. In acoustics, the decibel dB level of a sound is the formula D is equal to 10 times log of L over 10 raised to negative 12, where L is the sound intensity in watts per square meter, and the quantity 10 raised to negative 12 watts per square meter is the least audible sound a human can hear. Let's try this example. The intensity of sound a lawnmower is 10 raised to negative 3 watts per square meter. A. What is the corresponding sound intensity in decibels? How much more intense is this sound than the least audible sound a human can hear? So let's solve the problem. First, we are going to perform what is asked in letter A. So since the given L is equivalent to 10 raised to negative 3 watts per square meter, then substituting this value in our formula, D is equal to 10 times the log of 10 raised to negative 3 over 10 raised to negative 12. Now, applying the rules of exponent on quotient, we are going to subtract the exponent of the numerator to the denominator. So negative 3 minus negative 12. So negative and negative, that will be positive, or that will be plus. So negative 3 plus 12 equivalent is 9. Now the log or the common log of 10 raised to 9. So what exponent with base 10 that will give you 10 raised to 9? So simply it's 9. Therefore we have 10 times 9 is 90 decibels. For letter B, this sound is 10 raised to negative 3 over 10 raised to negative 12 is equal to 10 raised to 9, which is equivalent in values 1 billion times more intense than the least audible sound a human can hear. So, ganun kaingay po ang lawnmower. pH scale is another application of logarithm. Acidic and basic are two extremes that describe a chemical property. Mixing acids and bases can cancel out or neutralize their extreme effects. A substance that is neither acidic nor basic is neutral. The pH scale measures how acidic or basic a substance is. A pH scale ranges from 0 to 14. A pH of 7 is neutral. A pH less than 7 is acidic. A pH greater than 7 is basic. The pH level of a water-based solution is defined as by the formula pH is equal to the negative log of H raised to positive. That is the symbol or is the concentration of hydrogen ions in moles per liter. So ito pong H positive is the hydrogen ions or the concentration of hydrogen ions. Let's try this given situation. A 1 liter solution contains 0.01 moles of hydrogen ions. Determine and describe its pH level. Okay, let's solve this given problem. So since there are 0.01 moles of hydrogen ions in 1 liter, then the concentration of hydrogen ions is 10 to the negative 2. So itong 10 to the negative 2 is the exponential form ng ating value ng hydrogen or concentration of hydrogen, which is the 0.01. Kinonvert lang po natin siya to exponential form. So 10 to the negative 2 is the concentration of hydrogen ions that is in moles per liter. So substituting to our given formula ng pH, we have negative times the log of 10 to the negative 2. So by definition, log of 10 to the negative 2 is the exponent or yung value of exponent by which 10 must be raised to obtain 10 to the negative 2. So as by inspection, the exponent that will give the log of 10 to the negative 2 is, ito po, yung negative 2. Then, simplifying the given formula, we have negative times the negative 2. So, negative times negative, that is positive. Therefore, our pH is 2. So, the pH level is 2. Since the pH level is 2, then the solution is acidic. That's all for this session. Thank you for watching. Hope you've learned something.